Hello and welcome. In this tutorial I'll be talking about a miniuart block. So when you go to my site, you see I explain the inputs and outputs of the UART block. These are the pin descriptions. You go to my website, I have it there already. This is what the UART looks like. On your left hand side you have the different inputs and the outputs, and we also explained what each and every one of them do. These are the RX and TX clock, the data to send, the address, select, clear to send, and ready to send. So when you go to the site, you will be able to understand these concepts easily. Then I also explained some registers that were used also, especially this particular register, the word format register and the board format register. These are two very important registers that were used for this tutorial. So this is the second one, they call it board clock stuff. So these two registers, we need to master what exactly they do for the UART transmission. So I'll quickly go over to the logic sim tutorial. This is what the mini UART subcircuit looks like on the outside. This is what it looks like. So the UART always consists of a sender and a receiver. So let me briefly talk about the UART. I made a separate topic for it sometime last 2 years, so I'll just briefly talk about it. It's a mode of transmission, and it has the receiver and the transmitter. They are assumed to work independently actually, and they have board clock. The receiver does receiving, the transmitting does the transmission. So this, the same with this my UART, it does receiving and transmission independently. I will demonstrate an example for you. So you have the bit to receive and you have the data to transmit. So this is the bit that is being received, this is the bit that you are being transmitting. So you have ready to send and clear to send for the receiver and the sender independently. So when you are done receiving, after receiving, your data comes here as a data output. But if you want to send, you have to put your data in as a data in, then you'll be sending it. So it's more like a parallel to serial conversion. At your receiving end, you receive serial data and then you convert them to parallel data, while in sending you convert this parallel data here to serial data. So this TSD will be outputting signal every clock pulse. So these are the major bits we need compared to all this here. So that one is the major bits we need. They're the same. These ones are for the inputs and the one for the output. So I would like us to go inside, so I will explain what the different subcircuits of this miniuart looks like. I remember I said you have the transmitter and the receiver. So here, this is the transmitter. I've actually connected a clock to it somewhere down here, so you can find out that it has already started clocking. So I'll explain it as briefly as possible. The Velo code is very easy to understand. So this particular subcircuit here is the transmitter of the UART. So likewise, talk about the receiver. So first of all, this is the transmit clock, which I showed you earlier. I will describe to you in this tutorial how we generated the transmit clock. It's not the same with the system clock. The system clock is the one oscillating the registers. So now what it does first is we try to get the clock edge. We use the clock edge for precision, though it's not compulsory, but it makes the transmission more precise to use. So this is how we use it. This is what you are trying to generate here, the TS clock edge. So this is a very simple way to get a clock edge. You and the the clock pulse delayed by 1 clock cycle. So when you put a register here and a signal outside with a clock here, so the signal here is 1 clock pulse behind the one here. It's a very easy concept to understand for people who do sequential circuits. So this clock here is a delay, 1 unit delay of the clock here, because after the next clock cycle this one goes over here, after the next clock cycle it goes over here. So that's why the name TS clock delay is a delay in the original TS clock. So to get this clock edge, you are going to take that TS delay and add it to it the TS clock itself when it's off. So whenever it gives you a 1 signal, you get your TS clock edge. So that is how to develop this clock edge. We use it a lot of places during the tutorial, generation of clock edge. You just have to take the pulse when it's off, and then the TS clock when it's off, and then 1 unit cycle when it's on. You add them, you get a clock edge here. So now the clock edge will now be used for our counter, the TS clock counter. Now what does the TS clock counter? We use this TS clock counter because of this board format. When you go to the tutorial, this is where, let me explain the board format which I showed you guys earlier. Sorry for the, and this I made a little write up on it here. These are my write up on it. It's very small, so I made it more practical and less theory. Okay, so the board clock, actually here you can see if it's 00, it means you are using the original board clock. Divided by 1 doesn't really change anything. Then if that is this signal here, the BDF format, if it's 01, if it's 01, you are dividing the board clock by 16. If it's 10, you are dividing the board clock by 64. If it's 11, then you are resetting it. Then I made a calculation also here how to get whatever board clock you want to use for your UART transmission. You can do it using software actually. So the board clock you set here, the board format, sorry, determines what board clock you are using. Remember, they said when is 00, you are using the original transmit clock. You can see it here, the original TS clock is what is going to the multiplexer. Then when is 01, let me zoom in, sorry, you can see here when is 01, we are using the bit 3 of this counter here. So I already explained the counter. So what the counter does actually is just to count our clock edge. So whenever there is plus on the clock edge, it increments by 1. So it's just counting, incrementing continuously. So it takes bit 3. Now remember, in binary the first bit doesn't do anything. If you're reading bit 2, it's divided by 2. If you're taking, sorry, bit 0 is the same. If you're taking bit 1, if you're reading bit 1, you are dividing it by 2. If you're reading bit 2, you are dividing it by 4, right? And if you're taking bit 3 here, you are dividing it by 8. So this should be 1, 2, 4, 8, 16. Okay, that is it, right? This bit 0, 1, 2, 3. If this divided by 16, this divided by 8, this divided by 4, and this divided by 2. So then if you are taking bit 5, that means you are dividing by 64. If this is divided by 16, then this is divided by 32. Now this is divided by 64. So that is how we do the division. We do those divided by 16 and divided by 64 by picking different bits of the TS clock counter. So that is essentially what the TS clock counter does. It selects between the bit 3 and bit 5, and it represents divided by 16 and divided by 64. All this you will see it on your code. And then when it's 1 it means reset. When you out to whenever the signal is high, it means it's off. You turn it off by taking it to 1. So depending on what we set as our board format here, will determine what we are going to get at this output. Therefore, the output here is what we call the TS board clock. But here we call it TS board clock delay because we want to get the clock edge. Remember, I already explained something similar here when I did the TS clock. So we did it again here. So we take the pulse before it passes through. So let me reduce this. So it takes the pulse before it passes through the flip-flop, through the register, and then the pulse itself after it has passed through the register to get the TS board clock edge. Now you know what it got here was the TS clock edge and the TS board clock edge. So the board clock edge is what we'll be using for our transmission. Now this is the TX register delay, the TX register edge. That is, we want to get the transmitter for our register. I will explain the register in a minute now. So then you have the load bit. The load bit is used to load the data to be transmitted. So now this is the TS buffer here. This buffer is where the transmitted data first comes in during transmission, and for it to come in you need to turn it on using this multiplexer, and this multiplexer comes from this load. So this load bit is used to turn this multiplexer on. So whenever it comes on, it loads the data in. So this data in here will now load into this TS buffer whenever the load bit comes on. And remember, whenever the load bit comes, okay, so this TS buffer, what it does majorly is to advance our TS state, because down here I've highlighted it. You can see how it went here. So whenever it's 0, it advances 1 to our TS state, and it goes to the next state. So I will talk about that later. So now we have our TX data. So we have 4 different states. So the first one is the idle state. So I will explain it using our TX data. So this TX data is the actual data we are transmitting. So I'll explain what this multiplexer here does. So remember, I told you about the data going to the TS buffer. Immediately you press the load bit. However, you press the load bit also, that the TS buffer empty goes low and advances our state to the next state. It advances the state from state 0, which is the TX idle state, to the start state. So that's what the TS buffer empty bit does. So let's go down and we'll talk about the TS data. This particular multiplexer here, okay, let's talk about the first one, the reset. This is the reset line. So whenever it turns on, the TS data is constantly high, just like in every UART transmission. The line is always held high in a UART. Once the line is held high, it means it's inactive. So then until this next multiplexer is connected to the TS board edge, the clock board edge, so that this multiplexer, you can see the highlight, it went into almost every multiplexer here. So it's from here, sorry, the TS board edge, that's what we are using. TS voltage. So that's what's used for this particular synchronization. So I want to speak briefly on this TS data here. So this multiplexer here is being controlled by the state. It's being controlled by the state of the transmission. This is it here. Let me take you down so you see where it comes from. Here, it's controlled by the TS state, and now this is how the TS data, the bits to be sent, works. Now when the TS data, the TS state is 0, it is high, it's continuously high, is 1. The value of the TS data is high, that is inactive. And this is it here. This comparator also compares when it's 0. What does it do? It feeds down the TS register, the TS buffer into the TS register. Remember, this is the buffer here. This is the buffer. So at state 0, this buffer, let me highlight it, is going to come down through here whenever is in state 0 and send it to this register. So at state 0, things that happen at state 0 is that the TS register is being fed with the TS buffer while the TS data itself remains high. Then in state 2, that is when is equal to 2, it sends 0. The 0 is the start bit in every UART communication. 0 is used as a start bit, so it sends the 0 start bit in state 2. And for the TR register, when it's in state 2, that's when it starts sending the data. So each of the data to be sent this is a shift register, so it will be shifting 1 in and shifting out the data out. So assuming you have 1 0 1 0 1 0, so for every clock pulse, the TS register is shifting the data out and shifting in 1. So this is where it does that, this particular place, because whenever it's in state 2, this is where the comparator compares to know if it's in state 2. If it's in state 2, it turns this multiplexer on, and this is what happens here. When you go to the code, you understand this highlights more. A 1 is being fed in per clock cycle, and it's taking 7 to 16 of 0, 7 to 6, sorry, 7 to 1, neglecting B0. So B0 is always going out. It takes only 7 to 1 and then joins a 1 to it. It keeps adding another 1 to it. So the B0 now comes here. It goes here. You can see the 0 here, B0. And this is it also, B0. So 1. So at that stage 2, that is when the actual bit starts transferring. It transfers, so it's continuously transferring bit 0 of this TR register. So for every clock cycle, it's shifting. So the TR register is a shift register, shifting the bit out per clock cycle and using 1 to replace it. So the next state is the parity state, where it sends this parity calculation. The last state is the stop bit. Stop bit is represented by 1. Start bit represented by 0. So it sends a steady 1 to indicate that it is about to stop the transmission. So this is where the TS parity bit is generated. What it does is just to XOR all the bits. So for every bit that is sent out, you can see it takes that B0 also. So for every bit that is being sent out, this TS parity ORs it with the current OR result and keeps packing it until the right time before it pushes it in. So that's for the TS parity. Then we also likewise have the word format. When you go to the code, I did a little explanation on the word format here. Okay, yes, you can see it here. Let me cut this video now. I'll resume in the next video.